Yeah, mine yesterday said I need to do a backup. So yeah, luckily I did it yesterday.
Yeah, Claudia, are you ready?
Yes, let me share my screen. Oh, share this. Okay.
You see, Marcio, it's Linux, it's not Windows.
No, of course Linux. You know, I fell in love with Linux when the Slackware came out. So should I start? Or...
I think I have to do the introduction. Marcio wants that.
Okay.
He wants me to speak this terrible English before all the people. Yeah, they're going to find out. No, it's not true. No, you're mocking me, definitely. Okay, you tell me when to start.
Anytime.
Marcio? Okay. Hello, everybody. It was nice to meet you all here. We have a new speaker today. It's Claudia Lainscsek. Okay, I hope I pronounced that right. Claudia has been a friend for over a year. I think she spent a lot of time with me discussing about research during those pandemic times, which was excellent, great fun. Okay, Claudia gave me a small bio, so I'm going to read it for you, just giving some introduction. Okay, Claudia studied physics at the Graz University of Technology, Austria. And she's about to start her master's on plasma physics when she went to avant-garde art festival on chaos. Then she fell in love with it and brought chaos to the physics department. In '97, during a conference, when she was presenting the results of the Unsast library, she was invited to San Diego, California. There she was introduced to the idea of delayed differential equations for classification. At another conference in San Diego, she met Christophe Letelier, a common friend. It's incredible how small is the world. I know Christoph since 95, 94, but yeah.
He introduced us.
Yeah, long time ago.
Uh-huh.
And he became her advisor. Then she went back to Graz and finished her PhD. In the 99, she returned to San Diego and started developing the ANSAS library, DDA, and worked with the EEG data. She has been at the Salk Institute for over 10 years and has been working with the Sydney Cache, another coincidence. Marciu's working with the Sydney, I'm working with the Sydney and Vinicius as well, from Harvard Medical School since then. As she said to me, epilepsy data from MGH are the most exciting data I ever worked on. So Claudia, it's up to you now to give the lecture for us. Thank you ever so much for spending your time with us and give us a talk.
Thank you so much for the nice introduction, and thank you for inviting me and giving me this opportunity. So, of course, you know, I had to have my background with fractals because I love chaos. I since love chaos. So the talk will be, I will first show you what data I have. Then I will introduce you to my favorite analysis signal processing technique, delayed differential analysis. Have been developing this for over 10, 15, 20 years. Then I will show you how I apply DDA to seizures, how I can see chimera states in this epilepsy data, how I can extend DDA to assess information flow in the brain during seizures. So from where does the information come, how does it develop, and also go a little bit into prediction of seizures. So epilepsy, as you all know probably, is a chronic neurological disease in the brain that affects people of all ages. And 50 million people in the world have epilepsy. So this is one of the most common neurological diseases, actually. A seizure is a sudden breakdown of neuronal activity in the brain, and so you have involuntary alteration of behavior, movement, sensation, or consciousness. And if you ever knew anybody with epilepsy, they will tell you, okay, the medications are terrible. They have so many side effects. They're not fun to take. But they are lucky if it works, because there's a lot of patients for who the medication doesn't work. So the last resort then is surgery. So out of these 50 million people who have epilepsy, about 50% have focal epilepsy. And 30% of these patients, the medication doesn't work. Okay. So then the last resort is surgical resection.
I'm sorry, there's somebody with the microphone on. Alini?
And there's some feedback. Okay, so people go to the hospital. They get a lot of electrodes implanted. So I saw people with about 300 electrodes implanted. Usually it's about between, let's say, 50 and 120 is, I think, most common. But there's people who have 300 electrodes implanted in the brain. And sometimes they just keep implanting because the crucial importance is that you want to find out where does the seizure start, because you want to cut out brain. So you really have to be sure it really starts there. And if they're not sure, they just keep implanting. And these patients sit with, you know, all these electrodes in their brain in the hospital for a week, up to 3 weeks. And they hope they are having seizures. So they are hoping they have at least 3 to 5 seizures. So it's a very invasive and not very fun procedure. So the data I have, this is one of the examples. So here you have, do you see my cursor? Okay, so here you have deaf electrodes, and then you also have grid electrodes. And this is just a cartoon that shows, okay, here is the 2 grids, and then there's just 2 deaf electrodes. So what is delay differential analysis? So it comes from nonlinear dynamics, the idea that you have unknown dynamical systems. And then there's this cool physics Takens theorems that tell you that even if you have only a few recordings, that you these embeddings can help you get insight in the dynamics of the original system. So here's a time series. This is EEG data. So you can record EEG data or intracranial EEG data. Here's a little segment of this data. And here I plotted a delay embedding. So delay embedding means you take the time series and the delayed version of it. And you will immediately see that you see some interesting pattern here, which is not visible if you just look at the data. The other embedding is the differential embedding, where you take the time series and the derivative on the y-axis, and then you also get a pattern. And DDA combines these two embeddings. So if you're not familiar with embeddings, I have here a small presentation, a small movie. So this is one of my students saying the word iris. So this is iris. And here there is the delay embedding. And if I play the movie, then you see if it moves through the data, sometimes you really have nice structures like now. But sometimes it's also, there's very strange patterns. But the important thing is that for each sound or for each different kind of dynamics, you have a very distinct pattern. And the same happens in the brain. So if you have, for example, if you are in a sleep spindle, you have a different pattern than if you have a K complex. Or in a seizure, you have a completely different pattern. So delay differential analysis is done in the time domain. I'm not working in the spectral domain. And I'm using really sparse little equations called delay differential equations. So I have on the left side, I have the derivative. So I'm taking part of the differential embedding. On the right side, I'm using delays. So I have only 3 terms in this typical equation. X sub y means x of t minus tau 1. And this is x of t minus tau 2. So I have 2 linear terms and 1 nonlinear term. And the delays are not related to each other. They can be anything. And I will come back to that later, how I choose the model and the delays. And then, if I have this model, I estimate the coefficients A1, A2, A3, and the model error of this fit to identify dynamical differences in data. So I have, if I have the data, I end up with 3 and with the error 4 features to work with. So it's a really sparse, really little feature space. I'm not doing any pre-processing. So I'm not filtering the data. Excuse me. The only thing I do is I throw out amplitude information. So each data segment I normalize to 0 mean and unit variance. So then it is computationally fast because I have only a little equation and have just to estimate the 3 coefficients. It works, of course, for short time series because I don't have, I don't need a ton of data to just estimate this little model. And another advantage is if you have a small feature space, you don't run into problems with overfitting. If you have 100,000 of coefficients, of course, overfitting is a big problem. With 3 coefficients, it's nearly neglectable. And it's also noise insensitive because this little model just concentrates on the main dynamics of the system and cannot model noise as well. So I applied this, of course, to epilepsy, which I will show you. You can do sleep staging or look at different patterns in sleep. You can develop a biomarker for schizophrenia, which I did. I also looked at Parkinson's data. For Parkinson's data, I looked at EEG data. so surface EEG data and movement data. So I have this movement tapping. And then you can really see, okay, this person has Parkinson's and how fast is it progressing. I also applied this technique to heart data, so ECG data, for looking at differences between normal heart rhythm, congestive heart failure, and atrial fibrillation. I also looked at emotions in speech and dolphin echolocation. So this technique, basically, you can apply to anything where you have time series data. So how does this fit in with any kind of traditional analysis, and what are the differences? So for traditional analysis, you have your data. You do a lot of data pre-processing. So if you have EEG data, usually you want to filter the data. You have to filter out the line noise. You do, most of the time, you do ICA data cleaning. You want to get rid of blinks, of artifacts, of all kinds of things in the data. Then you blow up the data by computing your spectral features. So you have a really high dimensional feature space you're working with. Put it in a neural network or something to do dimensional reduction, and then you have your features to work with. DDA is a little bit different. It's a two-step procedure. So if I get new data like heart data, speech data, EEG data, I have to do the left step once. So I have to find a model that reflects the overall dynamical structure of the data. So in this case, I took ECOG data, so intracranial EEG data, just 1 second data segments, and I will show that later what I exactly did. We're feeding them into a genetic algorithm to find the best model and the best delays that had the lowest error for the model. And I found this model. And this model is actually really interesting. So I started with the epilepsy data, found this model, and then I did speech processing, found the same model. For the Parkinson patients, I found the same model. I found the same model for schizophrenia. So it's really a model that somehow reflects some dynamics of EEG data, of brain data. Of course, if such a small model cannot know everything about the data. So you have to ask specific questions. For example, is this Parkinson? Is this schizophrenia? Does a seizure start? Or things like that. And the way you ask that, you have to find the delays that answer that question. So after you did that, you can just get new data, don't have to do data pre-processing anything, and then you just feed it through this model and get your features to work with. Just remove amplitude information. So, and this thing actually compresses the data, because if you have like 1 second of data, 500 hertz, 500 data points, and then you get just 3 data points. So it already compresses it at a rate of 4 to 500. So I want to show you a little bit more how this works, how simple this is. So I have your data. This is a time series EEG data. And then you have your models. So you have your 2 linear terms and your quadratic term. On the left side, you have the derivative. So you do the time derivative, just, I usually do center derivative. The simpler the derivative algorithm you have, the better it is. You don't want to have any kind of filtering in the process. Then you have your other 2 time series. So I have the same time series. I have the squared time series. I apply the delays. So then I have a data window I can work with. Estimate my coefficients A1, A2, A3 with single value composition, and can look at the model error, just least square error. And then I move across the data. So it can be done very fast, and I think in real time, no problem. So next I want to show you how I use it for seizure detection, data segmentation. I will show you some Chimera states, information flow, and seizure prediction. So this is, so when I got the data, I had data from 13 patients, and then I did the structure selection. So I looked at every model up to order 4 nonlinearity with 3 terms, and there were about 280 models. And I took data segments from about 200 seizures, half an hour before the seizure and half an hour after seizure onset. Randomly selected from any channels, didn't care about artifacts, didn't care about anything in the data, just randomly selected a million of these data segments. And then I looked what models it found, and it was really surprising. So out of these 280 models, there was only a few models really often selected, 99%. And these models here, if you blow it up, have one thing in common. They have 2 linear terms and 1 nonlinear term. So that seems something that is really important for EEG data. Another thing that surprised me was that you have 2 models that are not very good models before the seizure, but after seizure onset, they are good models. So there's a bifurcation of some of these models. Of course, one of these 2, so this one model, 58, is exactly the one with the square term here. This model here has a power 4 nonlinearity. So of course, I had the choice to take one of those. Didn't matter which I take. Usually I take this model here with the power 4 nonlinearity. For the delays, if we look which delays are the best for each of these data segments, you again have a bifurcation. So you have some of these delays that are better before the seizure and some during and after the seizure onset. So then I, of course, chose here, I chose one of these models. This is this model. And here I chose this delay pair, which really show, which responds to this onset of the seizure. So how does it look like if I apply this to real data? So this is one of the patients. Here's the cartoon. This patient has 2 grid electrodes implanted and a few of deaf electrodes. This patient has 120 electrodes. And if I just plot the A1 of my model, then I see before seizure onset, I have one kind of dynamics. Then I have my seizure, which is here. And then after the seizure, I have a different kind of dynamics. I plot here 3 minutes before the seizure onset and 5 minutes after the seizure. Of course, you cannot see too much here about this, the channels themselves. So then I plotted a heat map where you plot the height of this plot as color. And here I have just the first grid, the second grid, and then all the deaf electrodes. And if you blow up this part of the plot, then you see really nicely where the seizure actually starts and how it propagates through the brain. Some patients also have subclinical seizures. So subclinical seizures are less than half a minute. They are really very localized and very short and hard to detect. So this patient had 2 clinical seizures and 17 subclinical seizures. Again, there was a grid implanted and a lot of deaf electrodes, especially here, these 2 deaf electrodes, 2 and 3. But you again see really nicely the structure. This is a seizure. And if you look at the heat map, you see that it is really localized in 2 of the electrodes and it's very short. You can also look at other things in the data. So there are stimulations. The stimulation, if you look at the heat map, looks completely different to a seizure. Also artifacts. Probably this picture a little bit looks like the seizure. If you remember, it looked like this. So, but if you look at the heat map, it's completely different. So during a seizure, you really have some distinct dynamics. During an artifact, you don't have that. And this is interictal data, which don't show too much. They're a little bit boring. So, and each time I plotted again 8 minutes of data. So then we had one patient where the neurologist told me 2 of the seizures start in this side of the brain, and 2 of the seizures start in the other side of the brain, and 1 is a broad onset. So there is 2 kinds of seizures and 1 is different. So this is not very pleasant for them because they really want to find out where does the seizure start. And it would be nice if it starts at one part of the brain, not everywhere. So when I looked at it, so this is the 2 seizures which should start here in this region. And these 2 are these 2 seizures which should start here in this region. And this is the seizure which should have broad onset. But if you look at all these 5 pictures, they all start at the same part of the brain. So usually the neurologists look at the raw data and they look at these tiny little spikes and they say, okay, there's the spike and so it starts here. But with this method, I see that all 5 seizures are the same. I found 2 additional seizures and one was after stimulation. Remember, this white stripe is the stimulation. And of course, again, Sid said, okay, don't worry about this seizure. We didn't tell you about this seizure because it's completely different. Seizures after stimulation are a complete different ballgame. But if you look at the seizure here and here, they are very similar. So even a seizure after stimulation starts in the same region and has a similar structure. This is a non-fully developed seizure, so it's probably a subclinical seizure as well. They didn't know about this, but it just starts also in the same region. So this is the patient 2 I showed you before, the subclinical seizure. So here you have these 2 clinical seizures. So again, both clinical seizures have the same pattern. And I think everybody without any training knows where the seizure starts. So this seizure starts here. So you have here these 2 deaf electrodes, 2 and 3, and they're very close to each other. And as you see, it starts basically here and here. And here you see it's a little bit less. But the subclinical seizures, you can also nicely see in this region. This one is in both of the regions, and this one, and they start a little bit earlier. So we are still discussing about these subclinical seizures, but they are a thing by itself. They are really hard to detect. They are just different. Let's put it that way. But the 2 clinical seizures are nicely to see. So then I had another patient, which was very interesting. So this is here, this is 4 days of data. This is hours, 150 hours of data, 160 hours, so 150 hours. This is 110 hours of data I started only here. And here are the seizures. You have these very distinct patterns before a seizure. So if I look at this, and it doesn't come up anywhere else in the data. So only before the seizures. And if you plot the phase, so I did Hilbert transform on the features, on the A ones. And then I really see really nicely something that comes up before each of the 7 seizures. And the interesting thing is it can happen up to 2 hours before the seizure. So and these are chimera states. So chimera state is you have synchronized behavior and desynchronized behavior next to each other. So before the seizure, you have here all these different phases. And in the non-onset channels, you have synchronized behavior. In the onset channels, you have desynchronized behavior. After seizure onset, everything is pretty much in a range of phases. If you blow up one of the seizure, you see they have these chimera states before. This is the Kuramoto order parameter, which shows you how ordered it is. So there is some kind of disorder, meaning there is some of these chimera states. And then it flips. You have also these micro events before you have the seizure. And then you have, then you have partly here, you have synchronization, then it desynchronizes, this synchronizes more. It's very interesting how this seizure has these different dynamics. And here the seizure ends and everything is quiet again. If you look at this patient had 7 seizures. So this is 30 minutes of data before the seizure onset and after, and you see always this chimera states before the seizure, and after the seizure there is nothing. Here there is a blow up 5 minutes before the seizure and 5 minutes after the seizure onset. This black line indicates where the neurologist said the seizure starts. And right now I'm actually discussing this plot with Sit Still. So this was published over a year ago. But there is these 3 seizures where the neurologist got the onset very nicely. There is these 2 seizures, these 3 seizures where you have a delay, but it seems to be also lining up. So what do I see? What is different from what they see? So we are discussing these things. Anyhow, I want to switch gear a little bit and how does this seizure develop? What is the information flow in the brain? How, from where does it come? How does, if it starts in some region of the brain, how does it propagate to the whole brain? So the big question is always, is correlation enough to infer causation? So can you just correlate a few channels and see, okay, they are doing the same, and so these are the onset channels and these are not the not onset channels. So the first answer about correlation and causation was in 1925. There is a fun paper written by Yule. Why do we get sometimes nonsense correlations between time series? So here he correlates the marriage rate with the death rate in England. They should not be correlated, but there's a strong correlation. Then he also points out that if you have a sine and cosine, of course, there's some causal interaction between those, but they are not correlated at all. But he already says that you have to use delays as well. So if you delay it by a quarter of a period, then you have correlation. A few years later, 41 years later, Granger published his paper about Granger Causality. It's a linear technique, so you have some kind of autoregressive model with and without the other time series, and then you compare the errors, and that way you can assess causality, Granger causality. It's a linear technique, and there is MATLAB toolboxes for doing that. But of course, nature is nonlinear, and linear techniques often have a little bit of problems. So here in this paper by Sugihara, he pointed out that there needs to be an extension to where Granger causality doesn't work. And this is based also on embeddings. So here is this our favorite toy system of everybody who ever did chaos theory. This is the Lorentz attractor, and is the 2 embeddings of the x and y variable. And you can assess causality by looking at these embeddings. So of course, after I was thinking, how can I extend this picture to causality measure? So here you have 1 time series, but I can look at 2 time series from 2 different regions of the brain. So my first idea was, if I have 2 time series, if I want you look at the delay, excuse me, if I have 1 times the delay embedding from 1 time series and the differential embedding of the other time series, can I infer causality? And I call this combination Cross-Dynamical DDA. So this was my first idea. Of course, I modified it a little bit. So if I have here a system A, which outputs a time series X, this could be one part of the brain, and it has a causal action onto a system B, which has another time series Y of T. So this could be another, so there could be two regions of the brain. So if I have my model here of X, as you saw before, I just put the error into the equation. And if I extend this equation by terms of the other system, which have nothing to do with A, then the model doesn't get better, because these coefficients are irrelevant. They are random and they don't change the fit of the model. And these two errors will be similar. On the other side, if I have Y of T and I apply my model and I take coefficients from this other system, which have information about B, then the fit gets better, my model gets better, the error should go down, and these two errors are not similar. So then I find the causal interaction from Y to X by just comparing these two errors. So I take the difference and the absolute value, and from X to Y, I take the absolute value of these two differences. So first, I try it on some toy system. So I simulated two networks of Izhikevich neurons. So you have excitatory and inhibitory neurons. And then one time network A inhibits network B, and one time network B inhibits network A. So I had the data I simulate are 4 seconds, 2 unconnected networks. Then I have block A where A inhibits B. Then again, disconnected networks, and then B inhibits A and disconnected network. And if I look at Granger Causality, Granger Causality gets really nicely these two segments and is zero everywhere else. Granger convergent cross mapping somehow gets it. It's not as clear as Granger Causality, and Cross-Dynamical DDA gets it as well. But here, this is half of this, and as you saw before, this network is just half the size of B. So I have a little bit of an advantage. I get also the double size. We have other examples where we looked at coupled Rössler oscillators and other data. Usually cross-dynamical DDA did better than the other techniques, but I don't show you, I show you only the results on epilepsy. So remember, we had classical DDA here. Everybody's already used to this picture. This is A1, and this is time. Here's the seizure onset. So you see this dynamics before the seizure, then the initiation of the seizure and propagation of the seizure and the offset. Again, here's the heat map. Here's the stars. These indicate the onset channels as determined by the neurologist. And everybody sees already, okay, the seizure most likely starts here. If I plot cross-dynamical DDA, so I take one onset channel, and then I look all the information it sends to everybody else, and all the other channels sending to this onset channel. So I looking at the communication of one of the onset channels to everybody else. And this is how much it sends and how much it receives. So it really communicates with certain other areas in the brain. And here's the heat maps. Again, you see it similar. You see the onset. This region also has some part of it where you don't see it too much here. But at the beginning of the seizure, there is a lot of communication between the channels. And during the seizure, there is not. So it's really at the beginning of the seizure, they really there's a lot of information flow that makes the seizure generalize. And here is again the cartoon. You have the grid electrode and you have the depth electrodes. The pink is just the background. And the blue circles are where the neurologist said this is the onset channel. Remember, patient 1 had seizures 1 and 2 should be the same, and 3 and 5 should be the same. In the classical DDA, we saw only this region as really onset region. But now we also see the second region where they said, okay, this starts here as well. So I plotted here as colors. I took this this peak here because this was very prominent, and take the value in this peak and plot it across the channel. So this is just a snapshot here at the peak of the data. Here, how much information it receives from everybody else. And you see nicely, I get these 2 regions where the seizure starts. If I look at the time, so each of these boxes is a quarter of a second of data, shifted by half of that amount, and the lower panel is the classical DDA. The upper panel is the information flow DDA. This is before the seizure, so not too much is happening. And then these 2 regions start lightening up. So there is information flow in these two regions. And the interesting thing is it comes up before classical DDA shows this region show up. So there is already there is already information flow before you can see it in a classical DDA. And it stays just in these 2 regions, the information flow, where for the classical DDA, you see the propagation through the brain. So then, so here again, this is seizure 1, as I showed you before. How does it change across the seizures? So if I look at seizure 2, seizure 1, you see it looks very, very similar. And if I look at all the seizures, then you have again, seizure 1 and 2 should be different than seizure 3 and 5. And this should be completely different. But all 5 of the seizures are very, very similar. And you see this information flow in these 2 regions. The neurologist pointed out that these are the onset channels. There is a green one here, which lights up actually in the classical DDA and here in the cross-dynamical DDA. And so I took it as an onset channel, discussed it with Izhikevich, and he said, yeah, you're right. This is an onset channel. We missed that. But it's very close in the region to the other channels. Anyhow, this is the seizure after the stimulation. And as you see, it's again very similar to what you have for the spontaneous seizures happening. So then I thought, okay, how well can I predict seizures? And there was a CAUSATION competition also about seizure prediction. And I did pretty well. So I was in the top 2% of seizure prediction for that competition. So these little DDE models seem to be working very well. Seizure prediction is very challenging because you have a huge diversity of epilepsy. And these DDA features show promise. So here's one patient. This is patient 3. I showed you that this is the patient with the chimera states. And since, you know, the chimera states are really prominent and you really saw that they only happen before the seizures. Again, this is 100 hours of data, and this is just 20 hours of data. Here I plot in blue, I plot an onset channel, and in red a non-onset channel, and I just subtracted the mean of both of them to have a baseline. But you see that you have very distinct dynamics only before seizures are happening, which doesn't happen anywhere else in the data. Here you have a similar behavior flipped. This is just, these are stimulations. They did some language mapping at the beginning of the recording. So this is completely independent of seizures, and it's also the other way around. So if you blow up, you again see very nicely where the seizures are happening, and you have a very distinct state before each of the seizures. This one is only 20 minutes long, and this one is 2 hours long. So there is a really long pre-warning for this one patient. So question is, can I predict seizures? Usually for seizure prediction algorithms, you have, you take half an hour before the seizure and say this is pre-ktal, and everything before that is inter-ktal. For this patient, this is not true, because here, if you just take half an hour and say this is pre-ktal, everything is inter-ktal, this is clearly not the case. So I did it a little bit different. I have a clinical onset. I block out 10 minutes after the seizure onset and don't use the data. Then I have my pre-ktal data 30 minutes before the seizure. And then I have 3.5 hours before where I say this is pre-ktal data. So this is something else. It could be pre-ktal data, but I do not know. So I just say, okay, this is a different state, and everything else is inter-ktal. So yellow is inter-ktal. For subclinical seizures, I block out 30 minutes before the seizure and 10 minutes after the seizure, and I don't use those data. I use only a pair of 2 channels and find the best channels for 11 patients where I can predict. So this is inter-ktal versus pre-ktal. Remember, this is this 3.5 hours before. I use a prime, the area under the ROC curve, as measure how well my, my seizure prediction works. So 1 is perfect separation, 0.5 is chance, anything above 0.7 is okay, everything above 0.8 is good, everything above 0.9 is excellent separation. So as you see, for these 11 patients, I got inter-ktal versus pre-ktal, very, very good separation, very good prediction. And 2 of these patients are excellent even. For inter-ktal versus pre-ktal, this is here, of course, it gets better because you get closer to the seizure. So everybody is very good prediction, and some are a very excellent prediction. So 0.8 is really good. So all of these are good. If I look at how is pre-ktal versus pre-ktal, yeah, it's okay. For some it's better, for some it's not. So this already indicates that you really have this half hour before the seizure to count as pre-ktal, and take the pre-ktal as inter-ktal does not work very well. And the next interesting thing is I always looked at 2 different channels. And if you look at these 3 regions, you see that here, for example, channel 80 is interesting for all this. This is channel 97. So you see common channels for the different tasks. So then I plot for each of these segments the area under the ROC curve. Remember, 1 is perfect separation. So if you have perfect separation, you don't have any chance of having a seizure soon. And here is again 100 hours of data, 4 days of data. And if I blow up this 20 hours of data, this is this perfect, you see really nicely, no chance, okay, seizure is coming, seizure really comes. It goes back to complete separation, so no seizure on the horizon, a seizure is coming, and so on. So all these 7 seizures have perfect prediction. Of course, this is a patient which is outlier. So this is how it looks for usual patients. Here you had a seizure and you had it went down. It did not go back to real baseline before the seizure in this period where there was no seizure activity at all. And again, on the x-axis is hours. So this is 160 hours of data. So during here, there is not, it doesn't go too much down. So the chance of having a seizure is not big. Here it goes down, and of course a seizure is happening. You don't have these extremely clear states. So I think if you compare these pictures, you would have to take more than one pair of channels into account. So this is seizure prediction. Out of the 120 channels or 100 channels you have, you only take 2 channels. So this is already very promising. But I also only used the classical DDA. I did not look at causality. So that needs to be done as well. But also, I think the most crucial thing is the length of the state should not be fixed. And it is different for different seizures in different patients. So you have to develop an algorithm that tracks these dynamical stage changes, even if there's chimera states in the data, which makes it much, much more challenging. So you have to have a really dynamic, a dynamic state detection algorithm. And this is what I'm developing right now. So I show you a few pictures and the idea how I'm doing this. So my idea is, I come from physics, so ergodicity is always a nice feature. Ergodicity means you take the time average should be the same as the ensemble average. So for seizures, if I take the overall dynamics of a region and compare it to the single dynamics of single channels, then I can assess dynamic ergodicity. And that way I can dynamically cluster regions in the brain over time. So remember, classical DDA worked like this. And to get the overall dynamics of the data, I'm doing DDA across time series. So instead of having here just one time series, I take just, here's the data, here's time, here's the channels. I'm taking just the segments of multiple channels. And then I estimate my coefficients. And that, of course, only works if these channels do the same thing. So if I compare then this classical DDA of each of these channels to what is the overall dynamics, then I can say, okay, do they belong to the same class of channels that have the same dynamics? Independent of phase shifts, independent of chimera states, independent of anything else. So I compare classical DDA features to these cross-trial dynamical features, to this overall dynamics features. And this is a new picture. It's not yet published and will be published soon. Hopefully in a few months I can tell you more. But this is this one patient where we had this long chimera states before the seizure. Here's the seizure. This is 2 hours of data. And here I looked at the clustering. So I took a part of the data here and clustered them. Okay, these channels are doing the same thing. I identified of them doing the same thing. So I just gave them an index how similar they are to this overall dynamics. And then for the remaining channels, I found another class of channels who were doing another thing. So actually I found 3 or 4 classes here, and I took the index as color. And then I do this dynamically clustering over time for this whole time series. And here, of course, it's nicely, it goes from blue to red. But here, before the seizure is onset, I have different states. I have different dynamics. I have a microstate before the seizure. I have different little things like that. And during the seizure, this is here blown up, I see that, some other channels suddenly do the same. And that changes during the seizure. And then something causes the seizure to end. So there is some of these other regions, which were actually here before, they are desynchronized. And that makes the seizure stop. But after the seizure, you do not see very much here in the classical DDA. But here you see, okay, I have regions where I have these together, then I have this region of dynamics, this region of dynamics. So the dynamics really changes a lot after the seizure. This is for another patient. And you, again, this is a few hours of data. You see, here's the seizure starts. Here, it's nicely, there is some different dynamics before you have a completely different state as during the seizure and after the seizure. So this is very promising, and I want to, so I'm developing this technique now that I can use it for looking all the seizures. So I have about 2,000 seizures to analyze. And you really need a fast technique to do that. So thank you. This was done with the Senersky lab at the Salk Institute. Many thanks to the Cash Lab at MGH. They are wonderful, they are great. Everybody's helping me so much. They invited me to Boston. I was there 2 or 3 years ago. It was very interesting to be in the surgical meetings, to really see the patients, to talk to people who are doing all this amazing work. Seizures are really, this data are really the most exciting data I ever worked with. And this is a picture at the Salk Institute where I work, and this is my group, the CHAOS group. Thank you.
Thank you, Claudia. Thank you for the very nice talk. I think we have some time for questions.
Oh, yes, please.
Okay. Any questions?
I got a few, but before I start, congratulations, marvelous set of data. One really fast question. These microstates that you found before the seizures, did you actually have a chance to look at the interictal period and see if these things appear without actually evolving to a seizure?
I'm looking at it now. This ergodicity measure is very new, and it's still in development, but I see it before the seizures. Now I have to go through all the data, and it didn't do that up to now.
Okay. One other question. When you decided to use 30 minutes as pre-ktal period, and then the pre-ktal of 3.5 hours, did you play a little bit with that time? I mean, what I mean is, it would be nice to see a graph that would show 10 minutes, 15 minutes, 20 minutes, 25, 30, 35, 40, up to an hour, and see if there is a point in which it really makes a difference in terms of the window that you have to predict. Yeah.
It's very different across the, so if you do that, we tried that, it didn't make too much difference because you have, it's so diverse. And I took the half an hour before, because in the Kegel competitions, you have this half an hour before the seizure onset. I tried it with 20 minutes, I tried it with 40 minutes. I got very similar results. And that tells me that it is diverse. You have for each patient, for each seizure, there is, for this perfect patient, sometimes this pre-ktal was 20 minutes, sometimes it was 2 hours. And that seems to be the rule. it is across patients and across seizures of one patient. It's very different. So you really have to have a procedure to detect the stage changes over time, and that's what I'm doing now.
So, because this has to do a lot with what has been recently being called the precision medicine. Precision medicine meaning that you would actually not have like this holy grail of treatment that would embrace every single aspect of epilepsy, but perhaps that you would find something that works incredibly well as a predictor for patient X that might not be the case for patient Z or another patient.
Exactly.
But this would actually mean that we should design prediction tools to individuals, not perhaps to the whole complexity of the system. But then again, having a method of designing that is equal to everybody. It's just that you're going to choose parameters that are different from patient to patient. That would actually mean that you have an incredible solution for predicting seizures. And the other thing is, one of the data that you showed that I loved, I liked a lot, is the data that shows that there's a really good argument that you have hypersynchronization between areas that way before there is a clinical onset of seizure. And when you showed that data, I mean, I'm not going to, well, it's one of your slides from the past. You said, look, although the seizures are different, you can actually see clusters with the 3 points here and the whole bunch of electrodes up here. And one of the arguments that I would make is that, okay, yeah, these areas are highly synchronized. It was way back in one of the, those. No, actually, a little bit up front. You just passed it.
Yeah, some are synchronized. Okay, here.
Yeah, so this is the summary of the synchronization, but you could actually show that.
So these have chimera states. See, this is the onset chance that have this chimera states, and here you don't. So here you have synchronization and desynchronization.
Exactly. So can you move some slides up front to the end of your presentation? You just passed the ones that I was actually going to correlate with this.
This one?
No, go ahead. Keep on going up front, close to the end. You actually showed that later, I think. Yeah. The ones, yeah, that's the one. So yeah, that's the one. Yeah, that's the one that you showed before. A little bit back. So yeah, one back. Yeah, that's the one. Yeah. So the one, yeah. So the one that you showed a whole bunch of them. So if you look at these slides, could you make an argument that what's happening throughout time is that you're actually silencing every other area? Not that you're actually increasing the connections between these 2 points and actually showing 2 clusters of beginning, but these 2 clusters, they kind of look like an attractor that actually drives every other information to them. But then one aspect of this is that you silence the activity of everything else. You can actually see that in the ones that you show the time evolution of this graph. There's one that's actually a whole bunch of blue. Yeah, that's the one. Yeah. So if you look at that, one of the things that I would actually argue is well, it does seem that you're silencing everything else, and then you have a clear cluster that appears from the background, as if this cluster was synchronizing everybody else and silencing everybody else and only maintaining specific structures that the neurologist would call the trigger zone, the epileptogenic zone. And that has a lot of implications with the research that we are doing right now, because what we are trying to do is to develop a certain invasive process of stimulating areas that would actually not allow this evolution to take place, not allow this attractor to actually overwhelm the network, all the other neurons. So I love this one. This one was one of my favorite results. Yeah. Well, anyway, yeah. So this whole idea of silencing everybody else, does this agree with what you?
yeah, we are still talking about this. So as I said, I need to go through about 1,000 more seizures. And we are right now, what actually we are doing right now, they have certain, okay, this is this kind of seizure, this is this kind of seizure, this is this class of seizure. So they give me the labels and they say, okay, patient 5, you only need to look at seizure 3 and 5, and next patient, you look at this period, and then show us the pictures. So right now we are on a level where they tell me which seizures to compare with each other. And then we have to make all these plots for all these different 2,000 seizures.
I know, but since you showed that there's a very similar pattern between them, and this was the most outstanding. So why don't you do some? Yeah.
Well,
So why don't you reverse engineering the process, meaning that you find the pattern, and then you look at the whole recording, everything. I mean, look at it from 0 to, I don't know, 300 hours, and try to see if that pattern appears. And when you look at that pattern appearing, then you say, look, this might be a seizure that started, but whatever there is inside the biological neural network, it was able to contain the seizure itself and did not blow into a behavioral seizure. So the neurologist would never detect that as a seizure onset because they didn't see the seizure happening. But for all means and purposes, the circuit almost sees. The circuit actually was evolving to the point where it would abnormally recruit the network and seize. But something happened, and it was able to block it. And that something might be what. So what I'm trying to say is find the patterns and see what happened right after the pattern that avoided that thing to actually. You might find some endogenous anti-epileptogenic zones. And these are the areas that should be targets of stimulating, or I don't know.
That's a great idea. That's a great idea. Thank you. Yeah, that's actually a great idea.
That's very close to what we are trying to do. Very, very close. It's just that when we trust too much the neurologists, we kind of think that they are actually giving us the gold standard. And to be completely honest, if that was the gold standard, I don't think we would have any problems in identifying patterns and identifying types of seizures. So there is something that they're just not seeing by looking at the raw data, that some techniques like this might actually enhance and show all this is noise and this is what's important. And I see this pattern happening over and over again, even when you don't have seizures. But every time that you don't have a seizure, there's a secondary pattern that appears. And that secondary pattern is what we're looking for, because that is the thing that's blocking the seizure. That is the thing that's avoiding the circuit from evolving to stability. Well, Claudia, I don't want to monopolize you. Thank you very much. It was marvelous.
I see in this patient, I also see a very interesting thing. So on top of these, small stage changes, I see that the patient is 100 hours in a different state. So I see a huge, it's just, there is additional activity in there. And all the 6 seizures happening, the fully blown seizures happening during this 100 hours. And the one who is not fully developed happens outside.
Yeah. See, that's the exception that you should be looking for. Exactly. That's what is actually, if I was looking for a cure, I would look at that one, because that's the one that actually the system was able to block by itself.
Yeah, and I also see one patient, he has actually 5 different states before. So there is a state, and if you have the grid like this, the seizures starts here. But the first state change happens up there, and then it travels through the brain. Some of these states are just 5 minutes long, sometimes some of them just 1 minute long, but it travels. So it seems to be different kinds of mechanisms how the seizure really starts. And the question is how many of these states are before the seizure?
So here's the thing. Here's our thought on that. Is that what they do have in common is that things travel, meaning that there is some kind of abnormal hypercoupling between the states that actually makes one generate the other and then the other, and the sequence is preserved. That's the other thing that we see. But what sequence, which areas, what kind of circuits? Well, that is very, very much patient dependent,
Yes.
and that's the thing that I think. If you're looking at some general aspect of looking at it, it's the hyper connectivity and hyper coupling making these transitions of state possible. So, yeah. Well, I don't want to. I don't want to make other people shy to actually make their questions. But thank you very much. This was very insightful.
Yeah, thank you. Thank you for inviting me.
More questions? Vinicius?
It was hi, Claudia. I'm Vinicius. I'm Eduardo's student. And I second what you said about Sid. He's great to work with, and he has a pretty awesome set of data. And I've been trying to work with DDA on both seizure and auditory test data from SIDS patients. But I was having a problem by choosing the right way to choose a model. I thought that was you had to pick up specific delays to capture specific frequencies, but after a presentation, I think it's more of a matter of optimization. So the algorithm does most of the work. So I wanted to know, like, what are the main challenges of choosing the right model to fit the epilepsy data, and perhaps other types of test data, of like auditory or visual test data. If it's all the same, like canonical or same default model, and you just adjust the coefficients, or if you must have different, widely different models.
So all I showed you here was with this exactly same model and same delays. But for the chimera states, we found that we have to adjust the delays for other patients to find also chimera states. The delays, they don't correspond to frequencies because you have a non-linear model. If you would have just a linear model, you would have a correspondence between delays and frequencies. Here you have a non-linear model, and the delays actually have no meaning, or I didn't find a meaning up to now. Does this answer your question?
Yes, yes, I think this. And about this patient that showed that the really clear chimera states, is there something remarkable about this epilepsy type or seizure types or seizure onset regions?
There was actually a lot of discussion about chimera states and if they happen in the brain. So we were actually the first who saw it in human data. There's in models and so on, you found these chimera states, but nobody really could show it really in EEG data before. So, but we found it only in one patient at that time. Now, when we are adjusting the delays, we find in more. And I also looked actually at spike data, so from the Utah array, data from the Utah array, and there I found also chimera states. So I'm finding more chimera states as I go, but it's very interesting that they are happening before seizures.
And one last question. Usually on SIDS data with stereo G recordings, you can have both the monopolar or recordings, but you can also bipolar re-reference across the electrode chain. So I have like new signals. do you apply usually on the monopolar derivation, or does it make a difference?
It does not make a difference. I played a lot around with it. I usually ask people always to give me the data as raw and unprocessed and unreferenced as possible. I just want to have I want to have data that come out of the machine. Whatever the machine does is okay, but I do not, I played with, everybody says, okay, you have to reference, you have to re-reference and so on. So we played a lot around with that, and it does not make a difference. The more raw the data are, the more unprocessed they are, the better they are. I do not even filter out line noise in my analysis. I do not do anything with the data.
That's really cool. I think that would be all of my questions, I think. Thank you so much, Claudia.
Thank you.
Oh, Claudia, just have a last question about computational demand. It's very hard to run DDA analysis, or is pretty fast. Can we do it online?
Yes.
And
so actually, we wanted when I was in Boston, we wanted to put it into a machine that people who are in the room looking at the patients, and they already look at the data while they are recording, to do it in real time. It's computational very, very cheap.
okay, so did you have already an interface for example,
so people at MGH have the code for analyzing epilepsy data. Right now, I'm teaching you to use DDA, and I'm developing actually a graphical user interface that you can just plug in your data and get the output. It will be available in the future, but if somebody wants to learn DDA, I'm always happy to teach it.
Okay, thank you. Any more questions?
Yeah.
Okay, that's it. Claudia, thank you ever so much for the nice talk. I hope we can call you some other time during the year for the new results that you have, and you can share with us in the near future.
Anytime. And if you need any papers, so most of these results are published. The last thing about Ergodicty is not. I'm just writing it up. So let me know if you need any preprints, or I'm sure you find it.
Okay. Thanks ever so much.
Yeah.
Max?
It was a pleasure.
I have to turn on the microphone. I'm sorry. I'm just pressing buttons here to see if I get the microphone working. Thank you very much. It was amazing. And Vinicius is one of our hopes for Brazilian science in the future, to actually mix in epileptology some of these mathematical models, and with Eduardo, mathematical models with the data that we get from our hospitals and neurological centers. So we have a very good center for neurosurgery here in Brazil. Vinicius works very closely with the neurosurgeon from our hospital, which is Sérgio Cansado. And I would say that we're still struggling, but the results are promising in a lot of sense. Perhaps we were too highly praised the results in terms of, we thought that we would actually find a fantastic answer and straightforward answer, but I would definitely say that we are making progress. And Vinicius is it's one of the very first students that we have here that dedicated his career in terms of such kind of modeling and such kind of data analysis. So it's a very good chance for us to actually get Professor Eduardo and Vinicius to work closely with you, which of course it's right within the helm of the things that we're trying to study in neuroscience. And and I would definitely say that this has applications to other models that we have that have nothing to do with the disease, have to do with how memory engrams propagate towards cortical structures, how memory works and stuff. So there's a lot of physiological things that might be fantastic for us to try to apply the DDR model too. So Eduardo, thanks very much for the invitation and for setting this up. Eduardo actually was the one that set the whole thing up, so it was fantastic. And Vinicius, great job.
Thank you.
Well, thanks, Claudia. Thanks. It was fantastic.
Yeah, show me. You should also show us your results at some point.
Oh, really? I'll let Vinicius and Eduardo share that with you. Vinicius actually published a paper just, I don't know, some 3 months ago, 4 months ago. In,
yeah, I sent the paper to Claudia.
Okay,
She already has the paper.
That is a modeling, a mathematical model of a lot of biological data that we have kind of within the same subject. So, and the whole idea here is to actually build a closed loop solution. That's the whole idea. So detect that the states are actually transitioning towards a dangerous situation of instability, and act on it in terms of driving it outside of these attractor zones. So try to drive it outside. And we are using non-periodic stimulation and some sort of external stimulation to actually be able to drive them away from these ictal states. And the other thing is, instead of looking at passive EEG, what Vinicius is doing, he's actually probing the circuit using, in his case, a non-invasive sound stimuli protocol. But I would definitely...
very interesting.
Yeah, and I'll definitely say that applying this to the model that you have, it's something that, well, Vinicius, you can talk a little bit about this, but this, I think, it would be incredibly interesting. Because by probing the circuit, you do not only passively look at it. When you probe it, you get these attractors to almost be able to trigger a seizure, but then they are readily self-controlled. But you do see the hyperconnections. So perhaps by looking at the data using your tools, we might see things that we missed using ours. Do you want to talk about this, Vinicius, a little bit?
Yeah, that's one thing I want to describe, because the auditory test that we are using involves steady states of potentials. And they elicit responses in pretty narrow bands. Like you modulate a sound, amplitude modulate a sound with 40 hertz, for instance, and you got a very clear response at 40 hertz. But I'm wondering if you have some, we are eliciting other types of activity, and if using DDA might help us uncover that, both on a passive case and both on a disactive probing for probing seizure concept zones, but also for probing across time if a seizure is approaching or not. And the second case, we have only one case, one patient from here. But for this probing for the seizure onset zones, we have a lot of data from Sid's lab and from here also.
Well, one thing, Claudia, that I think it would be interesting to add is that we have patients that we did the recording, we did an RF lesion of the areas that were the ictogenic areas, and we have post-surgical recordings. So we actually have very good controls in that sense, in terms of how these things act together. The idea here is very close to what you're trying to prove, that if there is some kind of abnormal coupling that changes states between A, B, C, D, E areas, could I give a sound stimuli on a very tiny electrical stimulation at one point, and actually detect that this hyperconnectivity is there even when the seizure is not taking place? I mean, the flow of information is somehow messed up. This information should be contained from flowing too much within the different areas of the brain, and something is just not blocking this flow of information. And that is the essence of why this circuit is so unstable. So the idea is if you do some active probing in the circuits, and Vinicius just using right now sound stimuli. But our idea in animals is to use sound stimuli, electrical stimuli, deep placed electrodes for electrostimuli. In England, we actually did this with a single pulse electrical stimulation. And but use visual stimulation, tactile stimulation. There's a whole bunch of other inputs to the brain that we can use to probe the system. And so this is where I think that your technique is I don't know, something that we have. It's a changing paradigm in what we were looking at, and I think this might be very interesting. And that's why, I mean, Eduardo caught this way before I did. I mean, Eduardo had to explain to me, like you explained a 2-year-old, why this was so interesting. But he did a very good job, I mean.
Thank you. I tried. Yeah, no, that sounds really interesting to look at this data. And yeah, you know, I'm happy to look at data. And Eduardo knows how to use DDA.
I hope so.
Just teaching him.
Yeah.
Yeah, I'm not fast at learning, but I'm trying to understand. That's it, Marcio?
That's it, my friend. I already talked too much.
Okay. So, Claudia, thank you ever so much.
Thank you. Thank you. No, it's interesting. I think it would be nice if we start a collaboration also, and we can look at data together.
That'll be great. Excellent.
Yes.
Okay.
Wonderful. Thank you so much for having me.
It was a pleasure. Thank you.
Thank you.
I'll see you guys then. Bye-bye. I think, Claudia, you can close the meeting because you are the host, aren't you?
I will. Okay. Bye.
Bye-bye. See you.